The recording didn't really work in the last lecture, so we'll see if it works today or not. But what difference, because we're at the end of the course. So, let's see. It's nice to see everybody here. Today's lecture will probably be pretty short. We're just going to wrap up the last topic and then call it. I looked at my notes for something else and kind of found out there was like no way it was going to fit. So I think we squeezed a lot into the semester, so we're probably good. In terms of announcements and reminders, hopefully you all remember by now that your projects are due on Tuesday. So I believe your presentations are on Tuesday and your write-up is Wednesday, yeah? And your write-ups are pretty much already done since you already made a first draft. I paged through everybody's first drafts, they looked okay. Which is good, that's why we have you do it. So there's that. And then, Thea and I will probably need a couple extra days to be on the end of that to grade, and then we'll be done for the semester. The turnaround for this class usually isn't too bad. In terms of stuff to do with the final projects, again, deadlines are important here because it really is, we've given you the last possible deadline in the semester by MIT handbook rules. So, we can't really provide extensions very easily. If we do, very likely we'll have to give you one of these O's grades in this course, and that's a whole administrative thing for everybody involved. So we'll try to avoid that, but of course, if you do run into a problem, it's no issue. But the first thing I will do, as we talked about before, is send you to S-Cubed or the grad office to confirm, because it's, I'm not a psychologist, I can't evaluate everybody's personal situation, nor do I want to. In terms of your final presentations, so Thea posted that spreadsheet where you've all signed up for time. Hopefully all of us have registered for time, yeah? At least those of you who are willing to look up. Yeah, and right, so before your presentation, I believe there's a slot on there to put a link to a Google Slides thing. So be sure to do that. And be sure to make sure that your Google Slides are publicly visible. You might want to even test it on incognito mode in your browser. So every single year, we end up in the same situation, which is the presentation works okay, but the student forgets to make the videos in their presentation visible, and then Google fails, and it becomes a whole thing. So we're gonna not do that this year. You're all gonna remember to put all the links that you need and test just once for me, please. Any questions about the end game for this course? I think it's pretty straightforward. Good, I've managed to wear you all out. You all look exhausted. Fantastic. So, it's the end of the semester, so we've done our job. Right, so the final lecture in this course, essentially it'll probably go on the short side, in fact almost certainly, because there's really not that much material left. We're going to wrap up our discussion of consistent mapping. And in some sense, it's a nice way to kind of wrap up this course a little bit, since we started with geometry in the small, right, talking about curvature and very small stuff. And now we're very much in geometry in the large, entire big data sets of shapes that we're considering all at once and trying to solve problems like consistent correspondence, which involves literally digesting the entire data set in one shot. This is not a problem that makes sense for a pair of shapes. And so to give you a bit of a reminder from our previous lecture, we spent most of our time, by the way, I think I kind of slid through quickly. I should give credit where credit's due. So this research, it goes back to this paper from Huang and Gibas in 2013, but I think it's one of the more foundational research papers in this area, is essentially considering this problem of I'm given sort of n objects, each of which is sampled with m points, and my goal is to find a consistent set of mappings from one to the other. Remember, consistency means that if I compose my maps in a cycle, I get the identity matrix. Right? So here our model for a map is just a permutation. And one thing to kind of keep in mind throughout all of these algorithms is that they're all kind of this is kind of a weird problem, right? Because the input to this algorithm is probably the output of some other mapping method. So it's definitely sort of one piece of a bigger puzzle, right? I don't know where you would get map data directly. So it is true that there's a larger problem to be solved, which is given a collection of shapes, compute the maps and make them consistent all in one shot, and that one has been a little bit less studied. But in any event, we followed through actually most of the math in this Wang and Gibas paper, and essentially what that led us to was a really interesting theorem. So our setup again is that we have this big matrix, this X here, which gives you this sort of permutation of points on every single object to every single other object. Right? So this is block matrix, where every block is a permutation. So remember, the diagonal is identity because that's the map from something to itself. By the way, there's a universe where it's not. If you had a symmetry, maybe you're already in trouble. And then we argued that this matrix is low rank, right? And remember, the high-level intuition for the low rank argument is that if my mappings are consistent, I can map everything to shape 1 and then back out. And so the rank had to do with the fact that really only the first row of that matrix, the block matrix rather, is relevant. The rest of it is just like products of the first row, right? And at the end of the day, that's what we argued. But unfortunately, if we wanted to solve this consistent map extraction problem, like finding the best approximation of an X, which is low rank, is non-convex because you need it to stay in the space of permutation matrices in every block. But we proved this convenient lemma, which is where we spent all of our time, or slightly less than all of our time, thanks to a slight improvement of a part of this proof. Thank you. Which is to prove 3 equivalent conditions that our mapping matrix is cycle consistent, low rank, which are sort of, these two are easy enough. But then this third one, which is totally surprising and weird, right? Which is that it's enough to check that this matrix is positive definite to know that all of the maps have to be consistent with one another. And that's weird because in the rest of this class, when we've encountered positive definite constraints, or semi-definite rather, it's been a relaxation. Like it's a bigger set than the one that we really care about. But in this case, like for whatever reason, this is sufficient. So actually the constraint that's difficult to enforce here is not the low rank part, it's the fact that X has to be binary. And that's the thing that we ended up relaxing. So that I think brings us to our story at the beginning of lecture today, which is we want to solve an optimization problem that looks like what's on the slide here. And let's make sure that we understand what's going on. By the way, I noticed in the end of lecture I squashed all of these slides into about 2.5 minutes, which is why we're going to just do them real quick. Right, so remember our input is a set of mappings between a bunch of different objects. That's what we're calling X in IJ here. And those mappings are not guaranteed to be consistent, right? They're just a bunch of mappings. It could be I compose them in a cycle and I flip left to right or something like that. We know nothing about it. And then our output is going to be this matrix X. And so if we look, we're trying to maximize the inner product of X, like the output set of maps and the input one. Can anybody come up like in words what this objective function is measuring? Remember that the X's are permutation matrices. Yeah, how much they resemble each other, but very specifically, right? If you think of like entries of these things with matching points to each other, and there's like a combinatorial way to understand this objective function, right? It's just counting.
Like number of common elements?
Yeah, so just a number of common matches between the input maps and the output maps. So essentially you pay every time you permute something. Does that make sense? Because of course the product of 1 and 1 is 1. Product of anything else and 0 is 0. So you pay because you're trying to maximize any time that your two permutation matrices don't agree, right? Because one of them will have a 1 somewhere where the other has a 0. That make sense? So notice that this problem is different than the ones that we set up earlier in our previous lecture. Like this can repair just one bad pair of points, whereas that lecture that we had, that method we had before with linear programming was trying to detect entire bad maps. Right, so this one's saying that like maybe our map is actually pretty good, but like these 3 points over here are messed up. Right, so that's what can go on here. Okay, so what are our constraints here? We're considering matrices X, which satisfy lots of different things here. So remember that Xij is like the IJ block, so this is mapped from maybe object I to object J. So let's see, can you guys remind me? So my matrix is binary and satisfies that a row and column sum to 1. And what kind of matrix do I have? What's that?
Orthogonal.
It is orthogonal, but it's actually, I can say more than that. Double-click stochastic, but it's binary, which makes it? Permutation, yes, sorry. I think 99% of you were right, and I heard one rotation in there, which is technically right, but we can do better. Okay, yeah, so X is by this constraint, and this constraint. Together, X is a permutation matrix. Now, this XII is equal to the identity, right? It's just saying that the map from a shape to itself is identity. Like we can pin that one. And then finally, we have this sort of doubly positive constraint that X is semi-definite. And if you recall, basically our lemma showed that all of these conditions together show that X is a consistent set of maps, right? That's what's hiding inside of this matrix X. And that's super weird, right? Because like essentially it's constraining X to be rank M, but you don't see anywhere a rank constraint here. And that was what's really shocking and surprising about the theorem we proved last time, right? I keep acting enthusiastic about this theorem because it's super interesting. Like this kind of thing never happens, and you guys are totally unimpressed. It's annoying me. Okay, right. So that's the way to view this. We're trying to maximize the number of preserved matches. We have a binary matrix. It's permutation. That maps our identity. We show that this is equivalent to being low rank in this very special setting. And by the way, like whenever you see a magic theorem like that, you really should ask like somewhere I'm paying for this. Like there's no way that like magic properties like this are true. And the kind of interesting thing is you're paying for it in this binary constraint, right? Because this is the hard one. So sadly, this is non-convex. In fact, it's not even differentiable if you have binary constraint. Like talking about convexity is kind of worthless. So we're going to do the same trick we've done a million times in this course, which is to say rather than making x either 0 or 1, we're going to constrain it to be in the range from 0 to 1. In fact, it's enough to just constrain it to be positive because it's less than 1 by these constraints here. And this is something we can solve. This is something you can code in CVS. Hopefully, by now in this course, having done the many homeworks, you're believing that this is not so hard to implement. Now, it's polynomial time solvable. It's an STP. We can solve this thing to whatever precision I want. However, is it particularly fast? It's just for a reality check really fast? This is huge. Do you see that? So like if I have 100 objects and each one is sampled with 100 points, then I have 100 squared. So I have a 10,000 by 10,000 semi-definite matrix as my variable here, right? Like this is like the product of all the unknowns and then squared. So this is a big problem to solve. But technically it's convex, so you can do it. And in fact, we can show that this procedure is often successful. So one detail here is, of course, we've relaxed to a real valued problem. So we have to round. I kind of skipped this detail last time. But the way that they get around that particular thing is now we can extract a given xij map, right? And what do we know? We know that it's doubly stochastic. So it's like almost a permutation, but it might have some like 0.7s in there or something. And so we need to round it off. So there's a different problem you might want to solve, which is find the closest permutation matrix to a given input. And that's roughly what I've put on the screen here. So here, x naught, maybe in this case, is just a single block of that bigger matrix. I'm sorry, the notation is a little ambiguous. So these constraints together make it doubly stochastic. I could add a fourth one, which is that x is binary, right? And then notice that this is kind of like just one little chunk of the big problem we had before. But this problem, it turns out you can drop the binary constraint, and you will still get a binary solution. You're guaranteed when you solve this in your program to get a permutation matrix. There are many ways to prove that, slightly outside of the scope of this course. But if you take any course on linear assignment, you'll justify it. I think the typical proof technique uses something called total unimodularity, which is a mouthful, but it's just some linear programming technique that kind of is giving you the corners of this polytope. But in any event, the basic point here is you can solve two complex programs. One that extracts something that looks close to consistent, and then you can kind of round off every block. And that's the procedure that they propose in this research paper. Now, some details. Let's say that I do this rounding procedure. I started with the solution of STP, and I got like some fractional value, so I did this rounding. And then I look at my collection of maps. Is it going to be completely consistent anymore? Turns out probably not, unfortunately, because this thing you apply to every single block of X independently. And it could be that this rounding procedure is what messes it up. And the hope is, of course, that it's more consistent than what you started with. Yeah.
At this point, this computation problem looks a lot like optimal transport.
It is exactly the optimal transport problem.
And then you say that we end up with binary solution.
Uh-huh.
What does it mean in the interpretation of optimal transport?
So remember in optimal transport, we briefly mentioned Brené's theorem. So, so fantastic question here, Tim. So the optimal transport problem looks like the following. We have man transport plan like that, and then the integral of your cost d pi, right? And so the way to think about this is you're solving a matching problem. In this case, like some infinite dimensional thing, and you've got this matrix of pi's, which is saying like how much stuff do I move from each point to every other point, right? So in general, this matrix, it's a matrix, but then there's a theorem, which in the smooth case is Brennier's theorem, which says, no, actually, you can understand pi as only having mass on the graph of a function. So it actually looks kind of like this very thinly sliced piece of this thing. So in other words, basically, you have to be a little careful because this isn't really a matrix. It's like some kind of continuum version. But like for every point here, it has exactly one point to which it puts all of its mass. Now, if you think about this linear program, it's sort of saying the same thing, right? Like my matrix is doubly stochastic, so it has the opportunity to put spread mass everywhere. But actually, that doesn't happen. You just end up with one target. And in fact, that's because these two theorems are basically the same. So it's a good observation. The fact that you solve this sort of linear programming analog of optimal transport, you end up with exactly the same theorem, which is that you don't spread mass nearly as much as your constraints might make you think. Abstractly, there's a reason for that. So if you look at the three constraints here, so this is a set of matrices, but it's linear conditions and then one linear inequality. Yeah. So kind of vaguely, sort of, you can think of this as kind of a polytope. It's like some weird thing which is cut off by a bunch of planes, right? Obviously, this is R2, and here it's like Rm squared. But abstractly, that's what's going on. And moreover, your objective function is linear, right? So it's just like a giant arrow sitting somewhere in this space. So in general, when you have a convex program and you're on a polytope like this is total digression, but if you're curious, this is how you justify this kind of thing. One thing you can convince yourself is that you're always going to have an optimal solution on a vertex of your polytope. So in other words, if you have all these faces, there's kind of never a reason that you need a solution here. It could be that there exists a solution here, if this arrow points right into that face, but there always exists a solution at a corner, right? And so a lot of convex analysis is all about what are the corners of a given polytope. So this object, this is called the doubly stochastic polytope, and guess what its corners are? So it's the permutation matrices. This is the convex hull of the set of permutations. So if you optimize any linear objective on this set, you are guaranteed to get, or you are guaranteed that there exists, I should be careful how I phrase that, a solution to this linear program, which is permutation. Does that make sense? Yeah. And so Brennier's theorem is some kind of continuum version of that. It's obviously a lot more complicated to prove, but spiritually it's the same. Yeah. Uh-huh.
Why do we have to do it in two phases? Why can't, is it possible to do it as one large?
It's a good question. The short answer is that we have no guarantee. So let's say I wanted, so the question was why do I have to do this in two steps? Could I take that second step and put it here? The problem is this constraint here, which we know is necessary to make that rank thing work out. But once I do that, in some sense, I've taken this polytope and I've added some curved thing to it. And so no longer do I don't know much about the corners of this set. And in fact, just empirically, you'll find that sometimes you run this, you don't get binary. Yeah, it's a downer. In fact, the semi-definite matrices that is a well understood polytope by itself, right? It's the convex hull of the set of rank whatever matrices. But here you're sort of intersecting it with a bunch of other stuff, and that's where you get in trouble. Yeah. But it's a good question. Yeah, it's somewhat tantalizingly close to the thing you want, but sadly not exactly. No.
Why can't you apply the same thing that we did with the rotation matrices and look at the decomposition?
You can. Yeah. I mean, you're saying if I got a high rank solution to this problem, can I do an eigenvalue solution or something?
Where we look at the Stiefel manifold, where we had a homework problem.
Oh, you're sure? Yeah, you absolutely could.
Okay.
It's actually historically.
Could you do the binary thing? Because it's going to be random.
Yeah, it's actually a good question. If I solve this problem, yeah, I guess I could have done all of this stuff, but instead of having the same W constraint, I could put the rank M constraint here. But that actually still doesn't solve your problem because it doesn't make this thing binary. So even if you're on the Stiefel manifold, you need something to differentiate. Yeah, so it's the binary constraint that really gets in your way. And neither of those strategies will give it to you. In fact, in a minute we'll cover a third strategy and we'll show it also runs into the same problem. Yeah. Somehow that's what's really weird about these map synchronization problems is it's binary that's the problem. It's not rank.
But once you're on the Stiefel manifold, you no longer need the positive definite.
You're right. So you get rid of that thing, but you still don't have you haven't solved the problem you wanted to.
Then it's
Oh yeah, but yeah. So you're right. You got rid of this thing.
Your your objective function is now not convex.
No, your objective function is linear. That's the same. What's
But
different?
We can compose it.
So I think what's different, so you're saying replace this with rank M.
Yes.
Cool. But that's still, so like the set of rank M matrices is itself some like weird curve, that's not even convex, it's like some weird shape sitting here, right?
Yeah.
So we don't know that the corners of this object are binary anymore. The only thing we know are binary is if you just have like these constraints. The second that you add another one, you're intersecting two convex sets. And it's actually quite annoying to like compute the convex hull of the intersection, like that kind of thing. Yeah. Yeah, this stuff is subtle and annoying. It's very easy to get stuck. But in any event, this procedure at least gives you a bunch of permutations, and oftentimes they are more consistent than what you started with. So there's a theorem that's in this research paper that is out of the scope of this course to prove because we haven't really touched on probability a whole lot. But essentially what they show is if you look at, so the way we've written down this problem here, there's, if you ignore the subscript on the sum here, this is like a sum over all pairwise maps. You could write exactly the same problem, but just do this on a subset. Like here, E is the set of maps that you have. Then this would like form some kind of a graph, right? Like where every vertex is like a different shape, and then every edge is like, do I have a map between these things or not? And so this thing has a Laplacian to connect all of the topics together in this course. This object has a Laplace matrix, and if you compute its first eigenvalue, this thing is called the algebraic connectivity, lambda 2. What's lambda 1, by the way? The smallest eigenvalue of Laplace operator. I hear whispers. And a weird hand gesture.
0.
0, thank you. Remember the first eigenvalue of Laplacian is 0, right? Because constant functions, Laplacian 0. So the second one's the interesting one. It's called algebraic connectivity. Remember like the eigenfunction there kind of splits the graph in half, sort of, that we talked about that a bit. So it turns out, kind of strangely, that like, this sort of gives you a fraction of your graph that you can get wrong. This theorem's a little hard to interpret, but they do one special case, which is when your graph is complete, because then you can just write down the eigenvalues of Laplacian easy enough. And in this case, it turns out that you have this really odd, shockingly coarse result, which says that like if 25% of the matchings in your inconsistent map matrix are garbage, and the rest of them are all consistent with a set of mappings, you will recover the full consistent set. So this is actually like a really shocking theorem. I mean, like I think there are very few algorithms out there that are resilient to 25% noise. But this is one of them. That said, I mean, usually when one permutation is wrong, like a bunch of them are wrong all at the same time because things kind of couple together. And I think it's probably partially where this 25%. Like this is not Gaussian noise, right? Like if I permute one thing out of the way, at the very least it swaps with one other thing, right? So it's very easy to get entire chains of things that are mapped incorrectly. Yeah?
But this is assuming you can solve the non-convex, right?
No.
It's not taking the Brown.
No, this is for the SDP.
Oh.
Yeah, if 25% of your maps are wrong, the SDP will give you a binary solution and it will be correct.
Okay.
Yeah, it's shocking. The proof is no fun. It's really long. I tried to cover it once and then we aborted halfway through. Yeah. But anyway, I encourage you to look. It's kind of funny because these folks published it in this little conference paper, this SGP conference, which usually has these little 7-page geometry papers, and then you open the appendix or like the supplemental document is like 40 or something. It's kind of funny. I don't know why they chose this venue. But it does appear to be correct. Many people teach this result. This is a well-known one. They also have some fun experiments. So here we have like the percentage of false matches and like the number of objects in your thing. And in fact, empirically, they find it even often does better. Like in their experiment, you can see that sometimes you can have a really large fraction of bad matches and this thing still recovers. But they can prove it for 25. However, how practical is this technique is a totally different question. And I think there's still, I mean, now you guys are all, like for instance, if you talk about Stiefel manifold or anything else, you're all equipped to reconsider this old research paper, and maybe you can do a better job of it. At the time, they didn't have that machinery available. These are the kind of results that they extract, where the mappings, this is a little bit misleading. We're showing 3D surfaces, but the reality is that the mappings are just at these points. So they like took a mapping tool and they just like sampled like 10 points per surface, or probably more than 10, I'm guessing like at least 30. And the mapping tools themselves are very inconsistent, but you can see here that this is a very it's interesting. It's a consistent set of maps, but it's not necessarily a good set of maps. You have to these figures are really hard to interpret, and I think it's easy to agree with them, and then you start looking at them critically, and you notice that there are things wrong. Like, for instance, if you look at this one, so like, if you compare the first two, what do we notice?
It's mirrored?
Yeah, it's mirrored left to right, but it's consistently mirrored. Meaning that like this person's right hand is consistently mapped everywhere to like everybody else's left hand. It's perfectly fine, so long as it's consistent.
It's actually mirrored on the feet, but not on the hands.
Oh, is that right?
Where are the feet mirrored?
Oh, you're right. Yeah, Shows makes a good point. So here, if you just compare the first two, the feet are swapped, but the hands are not.
The feet are the same. Green.
Green is green. Wait. Oh.
Yeah.
Oh, you're right. Yeah, never mind. No, I'm sorry. Something about that pose is throwing me off. Yeah, actually, wait. No, this is a perfect set of maps. No, yeah, I'm giving Qixing a hard time, but actually, his output is good. Here. I think. Wait, no, that's still correct. Never mind. Yeah, this is great. Yeah, no, this is just bad rendering. Okay. Yeah, see, look at how cool this algorithm is. It succeeded 100%. No, that said, there are cases where you can run this thing and it will extract a consistent set, but not necessarily a good one, where like you do flip things inside out, or God forbid you like somehow twist their torso 180 degrees. And as long as you do that in a consistent fashion, this optimization problem is happy. Got it. All right, any questions about this STP technique, minus the last 40 seconds of fudging around a little bit? Throw me off. Actually, I was already wrong. Okay, so this technique is, I think, to my knowledge, the one with the most theoretical analysis and guarantees. It's also related to a lot of other well-studied problems in this domain. Notice that it has a lot of structure in common, for example, with the rotation synchronization problem you did on your homework. Right, the difference there is that the rotation maps are really small. They're just angles, whereas here they're permutations. But up to that, these problems are almost identical. And so, in fact, I think the way that this theorem was proved was by kind of squinting at some papers on angular synchronization and borrowing their approach. There are some attempts out there to make this faster. So for instance, here's a research paper that appeared roughly at the same time on what they call permutation synchronization, but it's exactly the same optimization problem that's considered here. Amusingly, these were in two different communities. Like, you can even kind of recognize the paper template. This is NeurIPS, so all of you guys, many students in the room that are looking very tired are familiar with this paper template. But in any event, they prove something slightly different. So they say, okay, remember that I can write my mapping matrix. If it's consistent, I can say that it's equal to y transpose y. This is this result that we keep writing, right, where y is like the maps into shape 1, right? And so in particular, we can show then two useful results. So one is that X has orthonormal columns. Does anybody want to justify why this is the case?
What do we know about y? Or just any matrix y?
No. So X is specifically our binary pairwise consistent mapping matrix. So this is the thing we want. Then you can convince yourself that all the columns are orthonormal here. The way that you can do that is very straightforward. I mean, essentially, remember the schematic we had from our previous lecture that like there's like this little block matrix like this, where each of these things is a permutation, right? And so if I look at a single column of X, it's like this, right? And I compare that, I like take the dot products with like another column. It's sort of like taking dot products of individual, or certainly of Y. Actually, let's start there. And this is like taking dot products of different permutations, right? Just summed up. But we already know the columns of individual permutation matrices are orthonormal. And so at the end of the day, the columns of Y are orthogonal. This thing is a bunch of orthogonal matrices all in a row, so when you put them together, it stays that way. Moreover, the eigenvalues here of X are, maybe the right way to put it is is members of a set, which is clearly there's some zero eigenvalues because we've been arguing for like the last 2 lectures that this thing is not full rank. But it turns out there's only one other eigenvalue that it can be, which is n. Remember that n is the number of objects in our set. So let's justify that really quick. In particular, we can guess the set of eigenvectors of this matrix X. What do you think the eigenvectors are?
Probably relating to y.
Yeah, in fact, they're just y. So here's how we can justify this. So if we take x and we multiply it by y transpose, right? Then what is this thing? It's x, y. Oh, sorry. I already got it wrong. Oh, where are they? So x is equal to y transpose y. Y transpose, and let's parenthesize it like that. Okay. So what is y? So y, remember, is this matrix that like has little blocks that are permutations, like that, right? So what is y transpose? No, this is the same thing. Flip the other way. You know? So it's like taking. That's like what it looks like. So at the end of the day, this is equal to y transpose times the sum over I of xij xij transpose, right? Because that's, or whatever, you don't even need an I, just like a 1, right? Because remember y is just like the first row or column. Okay, what is this thing? What was that?
1.
All right. What is a generalization of 1 to bigger matrices?
Identity.
The identity. Right? So this thing is just the permutation matrix times its transpose. There's n of them, so this is equal to n y transpose. So if you kind of read from left to right, we showed x y transpose is equal to n y transpose. So in other words, all of the columns of y transpose are eigenvectors of x with eigenvalue n. Notice, by the way, if you didn't believe the claim number 1, you can kind of read it off of this thing, right? Because we now know that the columns of this thing are 1, and these are exactly a bunch of permutation matrices. Yeah. Okay. Yeah.
So if all your shapes are the same and the vertices are labeled the same, then all of the little squares in y should be identity.
Mm-hmm. That'd be a
So-
pretty lame consistent map
Yeah,
set,
but
but
then
yeah.
does x still have orthogonal columns in that case?
Oh, absolutely. Yeah. So let's. I'll prove it to you for the 2x2 case. Yeah. So in that case.
I guess my intuition was that x would be like all of the sub matrices would be identity, but then you'd have repeated columns.
You would have repeated, but you have to be careful which ones are the rows and which ones are the columns. I think is maybe where the confusion is. So y in that case would be like, oh, I already got the identity matrix wrong, shockingly. 1 0 0 1 1 0 0 1,
Yeah.
right? So then remember x is equal to y transpose y. You gonna make me do this?
You started.
You started it. No, just write that down. You can get some paper. You'll see it's real thoughtful. Yeah, this is a bunch of identities. No, I mean, all right. So y transpose is going to be identity. Y is really equal to identity, like that. Y transpose y is equal to I. Oops. Okay. So we do our matrix multiply. What are we going to get? Like that. Should I keep going? Okay. So this is. Let's see. Like that. Oh, I see. So your worry is that these two are not the same. Yeah, actually, you're right. I'm sorry. So what did I do wrong? Yeah. Oh, duh. Sorry. There. Prepared. Okay. There we go. No problem. Thank you for pointing out. Yeah, made a stupid mistake. Ugh, almost done with this class. Okay. Get to the tricky topics. Can we go back to differential geometry? I'm better at that. Okay. In any event, it's got just enough orthonormality that you can solve these problems. Thank you. And yeah, so what's proposed in this research paper is an even lamer approximation or relaxation of this thing. So what they do is they just say, okay, so what do I want? I want the max of x in, just like before. But now what we're going to do is say, okay, x has rank m and non-zero eigenvalues are all going to be n. So this is certainly a relaxation of our old problem. This is just like taking this thing and forgetting literally anything having to do with binary. My apologies, by the way, sorry. Michael. Okay, so this is a different problem you could solve. Any guess what this thing ends up looking like? By the way, notice that I can replace this with kind of 1/2. In fact, let's do symmetric for fun. Do we want symmetric? Actually, we don't want symmetric. Yeah, we do. Right, so we could replace x in with 1/2 x in transpose is perfectly fine. So like if we want, we can assume our input is symmetric. This ends up being an eigenvalue problem. Yeah, so essentially what you end up doing is you take v1 through vm, our eigenvector of x in with the largest eigenvalues, like that, and you write x is equal to u transpose, where u is equal to the square root of n v1 vm. By the way, if you read this paper, I know because I spent this morning reading this paper, their n and m is exactly the opposite of what Qixing's n and m are, which threw me off many times, but I think I got it right here. So they solve this thing, and then they do the same rounding procedure that we did for the previous paper. So these are two different relaxations, and they succeed in slightly different places. This one's a little bit weird because it's like not even close to having a binary constraint. There's not even an inequality here making this positive. If you read the paper, they do have a little bit of statistical analysis, but I don't know how. I'm not sure. So you guys should all read it and think like how realistic it is, because usually when you do statistics on problems with eigenvectors, it kind of ends up looking Gaussian because there's like lots of least squares looking things going on. But that's not the kind of noise that you really see in these synchronization problems. So I think it's a little tricky to interpret their theoretical result. But in any event, like if x in is away from x in like an L2 norm sense, like pretty close, then what they show is essentially like this U matrix, or like this X matrix here rather, it won't be binary, but it's close enough that the rounding procedure will succeed, right? That's the way they argue. So anyway, this is all to say that there's a lot of stuff out there. This procedure seems to work okay for some coarse mapping problems as well. I'm not sure if there's been a really careful comparison of these methods out there. And there's definitely more theory to be done. This is an interesting domain, and these are really hard problems. Have I managed to confuse you all yet? Because I can continue to make stupid mistakes. I'm glad I've got the police here today. Just give me a hard. I missed, there was the math grad student that was here for the first few lectures, and he really kept me honest, but then I think I was too snarky with him and I scared him out. That was my bad. Okay, so right, so that's our consistent map approximation problem. There's many solutions out there. I think when you look at this entire research area, for one, it's super interesting. It's a lot of fun. Like, these are interesting, mathematically deep results, and they're really challenging. There's a practical question you should ask yourself, which is, like, where's the input? Like, when do I have this big collection of n-squared things I don't want to fix? Like, in some sense, they're like kind of, they're putting lipstick on a pig, right? They got this, like, bad set of maths because our previous lecture got it wrong, and now we're trying to fix it. I mean, in some sense, we should just get it right from the start, right? And so there are some algorithms out there that try to glue together everything we've done in this course into one giant model and optimize for it. But as you might imagine, there's still a lot of room for improvement. So here's a really fun one. Proposed a couple years after this Huang paper we covered. which they call it a tight relaxation of quadratic matching. It's funny to see these things at geometry conferences because all these figures, they're very combinatorial, really. Like they show all these 3D models, but the reality is these mappings are really just the points because these are really hard optimization problems to solve. So here, right, so here's a kind of, this paper I consider to be like one of these things that like all of us would say out loud, but none of us actually tried, and then these folks did, and it does work. It's just wildly crazy to just implement and get this thing right. So here's the way that they do this. They say, okay, in an ideal universe, I'd like to have an optimization variable, which is a permutation matrix for every pair of shapes in my data set. Right? So if I have n shapes with m points each, already my variable in this problem is nm, is nm by nm, right? That would be like the size of that big matrix of all possible permutations, right? So that's like the variable in these problems. Okay, so now, what is the objective function in quadratic assignment? Well, it says like for, like if I have a pair of shapes, it says things like, if this point goes here and that point goes there, then I want these points to be similar distances. Remember we covered this 2 lectures ago? And that thing was quadratic in the entries of the permutation matrix. You remember this, kind of that story? Okay, so let's do some degree of freedom counting here, because it's just wild what goes on in this paper. I think it's really fun. So if you look at a lot of the different methods that we did on our homework, we actually applied the same trick more than once, which somehow looks kind of like the following, right? Like, essentially, you had some optimization problem which looked like, maybe 1/2 x transpose a x, such that, I don't know, b x equals c. Just generically speaking, we had a lot of problems that look like this, right? Just like quadratic problems with some linear constraints, maybe some quadratic constraints too, whatever. We introduced a big variable like this. Hopefully the story kind of abstractly looks familiar, right? And so then our problem became, ax such that b big X equals c little x, and I don't know, transpose, and big X equals little x transpose. Like you did tricks like this on your homework a lot, right? Where you reduce it to a linear objective, some convex constraints, and then like rank one thing. And then on your homework, what do? We just like slice that thing out, right? So if you think about it, what we did to translate from our original problem to this one is we essentially introduced a variable, like in big X, for every pair of variables in our original non-convex problem, right? Okay. With that abstract picture in mind, let's take a look at what goes on in this thing. So here, their variable in the original problem, not the relaxed one, is this matrix X, which is in 0, 1 to the nm by nm, right? Because this is the pairwise map between every pair of shapes, each of which is sampled with endpoints, right? And what they say is for every block of this matrix, we want to solve the quadratic assignment problem, which is itself quadratic in the entries of X. So if I want to apply this relaxation strategy here, so how many unknowns are in this problem? It's actually n squared m squared, right? Because it's all the entries of big X. If we want to use our SDP tricks from your homework then, I have to introduce a variable for every pair of variables in my original problem. So they do that like that. And so you end up with a semi-definite program where your variables are for every pair of variables and every pair of matchings in your entire problem. It's just wild that these folks tried this. I think it's so cool. Not the most practical thing, but really cool and interesting. And they show that indeed, when you solve this, you can do quadratic assignment between a ton of different pairs. You can add consistency constraints, whatever your heart may desire. And you really can solve this thing with a quadratic program, and with high likelihood, you will extract a bunch of binary matrices, as long as you're willing to wait, from now until the apocalypse for examples of size bigger than 4. But it's cool that they tried it, and super interesting. And to be fair to these authors, I'm giving them a hard time, but the reality is that they also have a lot of practical tricks for like shaving off constraints and seeing if you can do better than that. But anyway, if you kind of naively apply the composition of all the tricks we've seen in this class, you do end up in a formulation, and it's roughly what's here. There are other methods out there that try to be more approximate. So for example, these folks sort of make a conceit that like someday we're going to have to solve a quadratic piece, so they have this like sequence of quadratic programs that kind of converges to at least a local optimum of a problem that looks like this. A different way that you can go, which is actually some of my own old research, is to do consistent mapping in like sort of a low-rank matrix factorization kind of way. So you kind of ping-pong back and forth between, like so far we did an algorithm which we compute all our pairwise maps, then we compute the best consistent approximation, and then we stop, right? A different way you could imagine doing this is having kind of two sets of variables, like one set of bad pairwise maps and one set of consistent pairwise maps, and then trying to bring them closer together. And so that's sort of what's going on in this research paper. And if you do it just right, you can pose it as non-negative matrix factorization, which is kind of nice. Okay, so that concludes our discussion of the like sort of fancy convex optimization perspective on this problem. Now, for the last little bit of our class here, we're going to flip our perspective completely and talk about the other approach to consistency, which throws all of that out of the window and just does things on big data sets without worrying so much about guarantees. And in that universe, you can accomplish a lot more, at least practically speaking. Theoretically, it's totally unclear what these models are doing. It's really funny to present these results because like the last time I taught this class, these would have been considered like state-of-the-art, super cool things, and oh my god, cycle consistency is what's bringing them. Of course, like now 3 years later, everything is replaced. We know I'll do diffusion models and everything is out of date. I don't know, maybe in another 3 years it'll come back. It's hard to say. Okay, so the original research paper which proposed taking, and they even used the same terminology, like these are two communities that are adjacent to one another, proposed using cycle consistency in the computer vision setting was this thing from Julian and company. Philippe Isola has now moved from Berkeley and is a faculty member here. This was a generative adversarial network, or GAN, which made use of cycle consistency for these generative tasks. For like, here's a photo and I want like, the best version of this photo of a horse which contains a zebra. Like these kinds of problems. Like image analogies. So here's the basic issue in tasks like this. So there's sort of a lot of different tasks in computer vision, it turns out. But here's one very coarse classification of them, which are paired versus unpaired problems. And that looks something like this. So oftentimes we have these image translation tasks, and even in this setting, this isn't always so obvious. So like, let's say my task, and this is actually something I worked on years ago, would be like, I input a photograph of a cat, and I ask my software to generate a sketch of a cat, right? Now, there are two different data sets you might imagine for training such an object, right? One of them would be a big data set of pairs of photographs of cats and sketches of the same cat. But how big do you think that data set is likely to be? Well, cats maybe not. Maybe you could find it, but like, for a lot of categories, that would be a hard data set to find, right? Like, you need a very controlled experiment to have matched up pairs of the same photograph and a sketch of that thing, right? So in these unpaired setting, what you say is, well, maybe I collect a big data set of sketches and a big data set of cats, but I don't have a mapping between the two. Like, I don't know that this cat is this sketch. Does that make sense? And then, so that unpaired translation task is much harder. By the way, translation is the right thing here, right? Like, it's very easy to find lots of articles in English and lots of articles in French. It's very hard to find translations of the same article in English and French. When I say very hard, I mean like they exist, but like obviously it's a much smaller set. Yeah. Okay. So these generative adversarial networks are used for all kinds of interesting tasks, and one of them was exactly this kind of thing, like translating from one data distribution to another. And the kind of basic model that gets used in these adversarial networks trains two different objects, one of which is called a generator and one's a discriminator, right? And so in general, in your machine learning model, maybe I'm trying to translate horses to zebras. So like, here's a positive pair. Notice that these images look the same up to the horse-zebra difference, right? So one of these things, the generator, inputs a horse and generates a zebra. And then maybe in the old adversarial network, you would take the output, and the discriminator's job is to say, was this a real image, or was this one that was computer generated, right? And these are trained adversarially, right? As the generator gets better, the discriminator needs to work harder to figure out whether they're fake deepfakes or not, okay? But there's a problem with this basic model, which is illustrated on this slide, right? That if the question that my discriminator is answering is just, is this thing an image of a zebra, which is kind of the only question you can answer in these unpaired data sets, then it could be that you take every possible image of a horse, map it to the same zebra, and then your discriminator is perfectly happy, right? Like, okay, great, we succeeded. So this phenomenon is something that people in computer vision had complained about for a long time. It's called mode collapse. The basic idea being exactly what's illustrated here, right? Like your translation was successful in that it took every member of the set A and mapped it to a member of set B, but they had nothing to do with each other. Yeah? Okay. Well, in CycleGAN, they borrowed ideas from this geometry community that was doing cycle consistency and applied it to exactly this image task. And here is their basic point. I'm going to train two generators, one that takes things from set A to set B, another one that goes from set B back to set A. And now I can do the following. I can take my horse, convert it into a zebra, and I can convert it back into a horse, right? And so in other words, I have cycle consistency, at least in loops of length 2. And when I do that, I'm going to pay any time that the cycle doesn't close out, right? So this is exactly the kind of loss we've been considering in earlier parts of this lecture. So, indeed, CycleGAN's loss is really that simple. I mean, it's just composing these two things and then subtracting them to get the difference. One question you might ask, given all the work that we did in the first half of this lecture, I mean, there are all these different ways that we can write consistency down. Like, it would be an interesting question, like whether any of them can be adapted to this setting. I don't know of people that have done that. This is a thing to think about. But I think in some sense it's not totally necessary because these things are so non-convex after we've introduced a neural network that it's not clear why these like relaxations would really help you. But in any event, that's basically it. They leave the rest of the adversarial training alone. They just add this consistency loss and train these forward and backward translators at the same time. And notice that, by the way, this doesn't actually say that the map is particularly good, right? It just says that your map is kind of bijective. But apparently just by that and some of the what do you call this? Like what is this term people use? Like the bias of the fact that you're using neural network itself seems to create fairly nice images. So for example, here's some images from the original CycleGAN paper. We've got this horse here, and it can turn into a zebra. There's another one. Similarly for oranges and apples. Notice there's also an interesting, you can see some data set bias, like the leaves around the apple are changing too. It's not clear that that has anything to do with biology. You can do the same thing for, paintings. Like, obviously we don't have Monet and Van Gogh painting the same scene, but we do have collections of things that capture their style, and so now you can use this kind of technique to maybe translate images from one to the other. There are lots of interesting extensions of this work out there. So for instance, I mean, the original CycleGAN paper just considered two things. You could imagine like translator from set A to B to C, like for instance, in the previous example here, maybe I have, Monet, Van Gogh, Cezanne, and ukiyo-e, is that how you say? All at the same time. And now all of these cycle consistency ideas that we've been talking about come into play, right? I could cycle between these artists in all kinds of different interesting paths. And this is the setting where I think like maybe some of the low rank structure we talked about would be interesting. So in any event, there are a few papers out there that attempt this. They call them like cross-domain models. And it's kind of funny because you can see reflected in these things exactly what we've already talked about earlier in lecture, right? Like here are kind of two strategies for achieving cycle consistency. One of them is to enumerate every 3 cycle and then try to make them all consistent. The other one is to map them all to a central thing and back out. And indeed, if you look at the two dominant models for cycle consistency and GANs, you'll see that it's exactly those two. So no matter how things change, they all stay the same. So in any event, I think we'll probably we'll stop it there for once. We're early in this class, but the good news is that we've done so many lectures over that I think if you take the average, we're about right. So that concludes our discussion of consistent correspondence, which is one of these interesting sort of frontiers in geometry problems, and I think is really, in some sense, geometry in the large, right? Like this is considering big data sets all at once in an unsupervised fashion, and this is where a lot of the really interesting and hard open problems are. I mean, all the examples I think we see in this lecture are really clean data, for one. These are nice shapes, they have Laplacians, they're well behaved. The second that these things become messy, or they're not just bending and stretching, but like parts are missing, for example, to my knowledge, there are not very many algorithms that handle these particularly well. And that's really where there's a lot of interesting and open space. Like, for instance, if I run a car company, why is it that every time I make a new car, I have to start making a new 3D model of the engine from scratch, right? Like I have this big data set, of objects to choose from in the past, can I use that to inform the new object I make and map it on so that I recognize like patterns as I'm making new models? These are all exciting and new problems and ones that I think are relatively unexplored. In any event, folks, we'll stop our discussion there. Don't forget, on Tuesday, you need to come in and give your presentation. Please do not be late. Please, 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 practice your talk at least once with a timer. And how long should that take? 8 minutes. That's so little of your time. And if you're worried that that practice will take too much of your time, there's something wrong with your talk. Okay? So like, I just want to establish that now. This is an easy thing to practice, even if it's just the hour before class. I think you all can do it. So in any event, I will see you all on Tuesday. I'm very excited to see what you produce. In the meantime, have a lovely weekend. Enjoy the beautiful weather, and I'll see you then. All right. Yeah, stop this thing.